In this video, we're going to be discussing a special type of integral known as an improper integral. Improper integrals arise a lot in engineering, specifically signal processing, and in the field of probability and statistics. So an integral is an improper integral, the integral from a to b. It's improper if one of the endpoints a or b is infinite, plus or minus infinity, or if f is not defined at some value of x in the interval from a to b. So one of the endpoints is possibly infinite or minus infinity, or possibly the function is not continuous somewhere on the interval of integration. So for example, the improper integral from 1 to infinity, 1 over x squared, that's an improper integral because the upper endpoint is infinite. The integral from 0 to 1 of 1 over the square root of x, that is also improper because the function that we are integrating, 1 over the square root of x, is not defined at the lower endpoint. There's an asymptote there. And then the integral from 0 to infinity, e to the minus 2x dx, that is also improper because the upper endpoint is infinite. So here's what we're trying to do in terms of area. Let's take a look at the function 1 over x squared and the improper integral you saw on the previous page, the integral from 1 to infinity, 1 over x squared. Now what I've done is I've graphed the function from 1 is right here, 1, 1, all the way out to 10. And you'll notice that the function decays. What we're trying to do, we're trying to measure the signed area between x equals 1, the function, the x-axis, and all the way out to infinity, so to speak. So not just the area from 1 to 10, not just the area from 1 to 20, but the area to the right of x equals 1. So we're asking how much paint would I need to paint all that area in. Now you might think it's infinite. You might think that that area is infinite, but we're going to see that it's not. I mean, take a look at if we just go integrate from 1 up to 8. That's clearly a finite area. Remember, that's the 0.11 there. That's a finite area. Maybe the area from 8 all the way out to infinity is negligible. So that's what we're looking at. Similarly, let's take a look at the function 1 over the square root of x and the improper integral from 0 to 1 of 1 over the square root of x. Now 1 over the square root of x has a vertical asymptote at the origin, so the graph keeps going up like this. So when we write this improper integral down, what we're asking is there an area that corresponds to what we have here? Everything that's bounded by x equals 0, x equals 1, the function, and the x-axis. Now again, that's not obvious that that's a finite amount, because if we look at what's happening here, we might be led to believe that there's an infinite amount of area because of that asymptote, but we will see in a moment that that is not the case. So let's take a look at 1 over x squared, that improper integral, as x goes from 1 to infinity. Now what we're going to do is we're going to integrate it. We're going to look at proper integrals first. So we're going to integrate from x equals 1, maybe out to x equals 10, maybe out to x equals 100, and we'll just investigate what happens as that upper endpoint gets larger and larger. So let's say we integrate from 1 to 10, 1 over x squared dx. By the power rule, the antiderivative of 1 over x squared would be minus 1 over x. If we substitute 10 in, we get minus 1/10, minus what we get when we substitute 1 in, which would be minus 1 itself. So we'd have minus 1/10 plus 1, which is 9/10. So that represents the signed area between the graph, the x-axis, x equals 1, and x equals 10. What happens, let's say, instead of looking at the area just up to 10, we look up to 50. Everything's going to be the same, except that we're going to be substituting a different upper endpoint in. Now we'll have 1 minus 1/50th, which is 0.98. Let's measure the area from 1 out to 100. Same situation. Now we have a new upper endpoint. 1 minus 1 over 100 is what I'll actually get. That's 0.99. And we can see how these values are starting to get closer and closer to 1. In fact, what we could do is we could replace the upper endpoint of 10, 50, 100. Let's just put a letter here, b. 1 over x squared dx. The antiderivative would be minus 1 over x if we substitute b and 1 in. When x is b, we'd get minus 1 over b, and when we subtract what we get when we plug in 1, we would get 1. So it's really just these formulas up here, except instead of the upper endpoint of 10, 50, or 100, I'm using b. And now we can see that as b gets larger and larger, this gets closer and closer to 1 because 1 over b is getting closer and closer to 0. So we say that if the limit as b goes to infinity, x equals a to x equals b, if this limit exists and if the limit equals L, we say the improper integral converges to L, and we write this way. The integral from x equals a to x equals infinity, f of x dx equals L. So the new word is converges to L. So if the limit does not exist, we say that the improper integral diverges. So in the preceding example, we would say that the improper integral from 1 to infinity of 1 over x squared, because the limit of this is equal to 1, we would say that this improper integral converges to 1. Now here are the steps for determining whether an improper integral converges if its upper endpoint is infinite. We first replace the infinity symbol with a parameter. Call it b. Doesn't really matter. Just you can call it b. Evaluate the proper integral from a to b, and this is going to yield a formula involving b. And then we take that formula and we calculate the limit as b goes to infinity. If that limit exists and equals L, we know that the integral converges to L. If the limit does not exist, the improper integral diverges. So let's take a look at an example just to go through, going back to the integral of 1 over x squared from 1 to infinity. Okay, it's an improper integral because the upper endpoint is infinite. So I'm going to write the limit as b goes to infinity, the integral from x equals 1 to x equals b. So we always start by taking that improper integral and writing it as a limit of proper integrals. Now we're going to focus on what we have in here. We're going to compute the antiderivative of 1 over x squared, substitute our endpoints in. So the antiderivative of 1 over x squared would be minus 1 over x by the power rule. We substitute b and 1 in. We have the limit as b goes to infinity, minus 1 over b, minus what I get when we substitute 1 in, which would be minus 1. So we have the limit as b goes to infinity of 1 minus 1 over b. Now it's important to use good limit notation here. Notice how I'm writing the limit as b goes to infinity at each stage. We're not just going to say at this point, we're not going to just say 1 over infinity because infinity is not a number. But as b gets larger and larger, this quantity becomes as close as we want to 1, so the limit is equal to 1. So in this case, we would say that the improper integral from 1 to infinity of 1 over x squared dx converges to 1. So that means, how much paint would I need? How much paint would I need to paint all of this area? On the surface, the amount of paint seems infinite, but I would only need 1 unit, or 1 gallon. Now let's take a look at a slightly different example. The improper integral from 1 to infinity of 1 over x. So I'm simply changing this from 1 over x squared to 1 over x. The process is exactly the same. The first thing we do is we write our improper integral as a limit of proper integrals. So I'm going to replace this upper endpoint infinity. I'm going to replace it with, let's say, a b. That's a b. It doesn't really matter what letter you use here. I'm going to just use a b though. So now we need to evaluate this integral, and it's going to give us a formula in terms of b. So the antiderivative of 1 over x is the natural log of the absolute value of x. And notice I'm still going to leave the limit as b goes to infinity out here. Now I have to take this antiderivative, substitute b and 1 in. Again, I'm taking the limit as b goes to infinity. The natural log of 1 is 0, so I'm left with the limit as b goes to infinity of the natural log of b. We have to ascertain what happens in this case. It is quite common when we work with an improper integral at this stage to evaluate this limit that you need to look at a different graph to help you ascertain whether the limit exists. So in this case, I'm going to look at the graph of the natural log function and look at what happens to that function as the input becomes larger and larger. So here's the graph of the natural log function. I'm labeling my axis b. There's the natural log of b. Now this function has an asymptote at the origin. As b gets larger and larger and larger, the natural log curve grows and grows without bound. There's no horizontal asymptote. The natural log curve keeps going up. There's no asymptote. It keeps going up forever. So we would say the limit as b goes to infinity of the natural log of b, that limit does not exist. And because that limit does not exist, we say that the improper integral from 1 to infinity, 1 over x dx, we say that that improper integral diverges. So notice how simply by changing this from 1 over x to 1 over x squared to 1 over x, now we get an improper integral which diverges. So in terms of the graph, that's saying here's 1 over x from 1 out to infinity. Now we're saying that how much paint do I need to cover all of that? Well, I need an infinite amount of paint. Whereas for 1 over x squared, a finite amount of paint. And we can sort of see that if we compare the two graphs. Let's take a look at a different type of improper integral. Let's say the integral is improper because the function is not continuous at the lower end point. We do a similar sort of thing here. We first replace a with some letter different from b. So maybe the limit, I'll replace a with c or something like that. You just don't want to get your letters confused. Evaluate the integral from c to b of f of x. This is going to give you a formula involving c. So we're going to change this to a proper integral. We're going to calculate the limit as c goes to infinity. If that limit exists and equals L, we know that the improper integral converges to L. Otherwise, the improper integral diverges. So let's take a look at an example. This was one of the improper integrals from before, 1 over the square root of x dx. This is improper because the function is undefined at the lower end point, which is 0. So we're going to replace that 0 with something else, like a c. It doesn't matter if I use a c or a b, just some letter here, and then take the limit as c goes to 0. Now why are we letting c go to 0 but not infinity? It's because the bad point is x equals 0. This is not an improper integral with an endpoint of infinity. We're going to do exactly what we did in the preceding approach. We're going to evaluate this. We're going to get a formula in terms of c, and we're going to ask ourselves what happens to that formula as c goes to 0. Now this is the same as x to the minus 1/2. We're going to integrate this by using the power rule. The power rule says that the antiderivative of that would be 2x to the 1/2. We're going to evaluate that at x equals 1 and x equals c and subtract. Notice how I'm still putting the limit at each stage right here. If we substitute 1 in, we get 2. 2 times the square root of 1. If we substitute c in, we get 2 times the square root of c. And we want to know what happens to this as c goes to 0. Now again, here's a situation. To get a handle on this limit, it's going to help us to take a look at a separate graph. I'm going to look at the graph of the square root of c, which is right over here. And I'm going to ask myself, what happens to the square root function as c gets closer and closer to 0? Well, the square root gets closer and closer to 0. If c is 0.1, the square root of 0.1 is close to 0. So if c goes to 0, this all goes away and we're left with 2. So this is not the graph of the original function, but it's a graph we use to help us evaluate the limit. So in this case, we say that the improper integral from 0 to 1, 1 over the square root of x dx, that converges to 2. So in terms of area, we're saying that if I look at 1 over the square root of x and I want to find how much area there is between 0 and 1, the curve and the x-axis, there is exactly 2 units of area. That's not at all obvious from the picture. Here are some examples for you to try. Determine whether each improper integral converges. If it does, state its value. The integral from 1 to infinity, 1 over x to the fourth. The integral from 0 to 1, 1 over the cube root of x dx. Make sure that you use limit notation correctly. Okay, so in every one of these problems, there's going to be the limit, maybe as b goes to infinity or as c goes to 0. There's going to be the limit at each stage. Don't be doing arithmetic like 1 over infinity, something like that. Infinity itself is not a number, so make sure to use good limit notation.